Have you ever seen a high-quality portable food dehydrator? Well, meet Forest. Forest is made out of marine plywood with a dimension of 31 by 28 by 47 centimeters that comes in a detachable 4 wheels for easy use and transport. For its exterior, it has a triple-coated dark green paint which makes its appearance look vibrant. It has concealed hinges and silver-painted plastic handles. Its wirings are encased in plastic moldings for aesthetic appeal and to prevent entanglement of wires. For us to monitor certain parameters, it has 2 hygrometer with mini LCD display of humidity and temperature, and a temp controller with onset and offset temperature. It has kilowatt-hour meter with 16 amperes that displays voltage, current, power, and energy. Now, let's take a look what's inside. Forest has 4 aluminum grill net trays with a dimension of 29 by 26 centimeters. It has a range of 220 to 240 volts of fan and 2 220 volts PTC heaters. Again, that's Forest, our forest.
This project aims the students to learn about the electrical connection through simple wiring, switching and disconnection, power calculation and consumption monitoring, and to apply basic engineering efficiencies in terms of cost, energy utilization, and throughput. In the development of the dehydrator, the team embarks on a thorough research delving into existing dehydrators to generate valuable insights into design features. Sketches and diagrams were proposed related to innovation and feasibility to ensure that the proposed dehydrator aligns with the project's goal. The team then procures materials and components for the electrical wiring, assembles the dehydrator, and conducts functionality tests. During the functionality test, a problem was encountered with the heater, which was fixed by replacing the heater. The project then undergoes a dehydration test on eggplant, banana, and chicken samples, ensuring the required temperature window is reached. The dehydration time and temperature are researched and based on industry's best practices, taking 3 days to complete. For the first day, the team tested a banana sample following the recommended drying time and temperature of 6 to 12 hours at 57 degrees Celsius. The initial test yielded poor results, prompting an increase to 65 to 70 degrees Celsius for 9 hours. The kilowatt-hour meter showed stable voltage, consistent power supply, and energy consumption. For the second day, the team successfully dried a jerky sample of eggplant by adjusting the temperature to 70 degrees Celsius and 75 degrees Celsius, slightly higher than the recommended 4 to 6 hours. The process resulted in decreased humidity, stable voltage levels, and stable energy consumption with fluctuations during controller changes. For the last sample, chicken jerky, the chicken was marinated overnight for flavor and pat-dried to reduce excess liquid. The suggested dehydration time and temperature for chicken jerky is 4 to 6 hours at 73.89 degrees Celsius. Therefore, the team decided to adjust the temperature to an onset of 85 to 90 degrees Celsius. Throughout the dehydration process in this sample, the kilowatt-hour meter shows constant voltage, indicating reliable power source and temperature control effectiveness despite fluctuations in power and current. It is also showed constant energy consumption with display measurements resembling theoretical values.
Our group chose eggplant as a dehydrated vegetable sample due to its availability and cost in the local market. We considered the sample size per kilogram that would fit in the DIY dehydrator. Before dehydration, the eggplant was sliced, marinated overnight for flavor, and pat-dried to reduce excess liquid. Following Jerkaholic's recommendation, the marinated eggplant was supposed to be dehydrated at 62.78 degrees Celsius for 4 to 6 hours, but due to challenges faced in the dehydration process, the group decided to adjust the dehydrator temperature to an onset and offset of 70 to 75 degrees Celsius, slightly higher than the recommended temperature. Additionally, the group prioritized cleanliness, ensuring hands and equipment were cleansed before washing and slicing the eggplant. The slices were arranged on a dehydrator trays with space for airflow.
For the fruit sample, we chose to dehydrate bananas, specifically the Lakatan variety, because it is a common banana cultivar that is widely available in the market. The suggested dehydration time and temperature for bananas is 6 to 12 hours at 57 degrees Celsius. To dehydrate bananas, first, peel and cut the bananas into 1/4 rounds. Then, arrange the banana slices in a single layer on dehydrator trays, ensuring there is space between pieces to allow airflow. Then, dehydrate bananas. On our first test, we followed the suggested time and temperature and dried the samples for 8 hours. However, we were not satisfied with the results because we did not achieve the quality that was expected. Because of this, we repeated the test and increased the drying time and temperature to 65 to 70 degrees Celsius for 9 hours. Thankfully, after the second test, we were able to dry the samples successfully and produce dehydrated bananas, which was indicated by the decrease in the values of the inlet and outlet humidity, and the values that were obtained are somewhat near. We also tried the break test to check its crispiness. Furthermore, we highly recommend extending the drying time to achieve a crispier quality.
For the meat sample, we chose to dehydrate chicken given that it is widely available but also cost efficient than pork and beef. Specifically, we chose the chicken breast because not only is the best part but also the easiest to slice into strips. Compared to pork and beef, chicken is a little more tender and takes better flavor. It also serves as a challenge on our dehydrator since it requires high temperature and if our PTC heater can still keep up in this test. Prior to dehydration, the chicken was marinated overnight to add flavor for the jerky and was then pat dried to reduce excess liquid that can affect the dehydration process of the sample. It is recommended that the marinated chicken to be dehydrated at a temperature of 73.88 degrees Celsius for 4 to 6 hours according to Jerkaholic 2020. To dehydrate the chicken, wash and slice the chicken breast into thin strips. Then, arrange the chicken strips in a single layer on a dehydrator trays, ensuring there is space between pieces to allow airflow. Happily, we were able to dry the samples and make a chicken jerky. Furthermore, we highly recommend extending the drying time to achieve the best result and make sure to rearrange the position of the trays in order to fairly dry the samples.
Power is calculated as the product of voltage and current. Based on the tabulated data displayed for the voltage, current, and power of our dehydrator, through calculation, it can be observed that although there is a slight discrepancy in our results, it still can be assumed as accurate. Additionally, prior to the procedure, our group checks and calibrates our dehydrator to ensure an accurate and consistent display of our data.
In order to increase the efficiency of the dehydrator, use ingredients which are thinner and have less moisture content to speed up the dehydration process. To reduce energy consumption, we can use electrical components which have a lower power rating. The lower the wattage, the less energy the dehydrator will use. However, it will take longer to dry the food. Ensuring that the dehydrator is working at an optimal condition, as well as setting the right dehydration temperature, is also a factor. A timer to switch the dehydrator on and off will help save energy and properly dry the food without cooking it. Aside from this, we can dehydrate large batches of food at one time and run the dehydrator less frequently to prevent it from being exhausted.
The main challenge that our group encountered was the inaccurate reading of temperature by the temperature controller module because its sensor is placed near the heater, so the values obtained are slightly higher than the actual temperature inside the dehydrator. In order to address this issue, the use of an inlet and outlet hygrometer is very helpful because it also gives temperature measurement aside from humidity. This is the reason why we slightly increased the drying temperature because there's a discrepancy between the measured and actual temperature to ensure that the sample was drying properly. Aside from this, there had been also a problem in the documentation of the dehydration process. The video clips that were taken were not continuous throughout the test due to technical errors such as power outage in the phone that was used in taking the videos.
For the project insights, our food dehydrator is an equipment designed to extract moisture from foods to prevent the growth of bacteria, yeast, and molds. It allows us to naturally extend the shelf life of food without the need of any preservatives. In this project, we were tasked to stimulate our participation and critical thinking while applying our knowledge on electrical connection through simple wiring, switching, and disconnection, as well as power calculation and consumption monitoring. In addition, we applied basic engineering principles to increase the efficiency of our project in terms of cost, energy utilization, and throughput. The development of a portable food dehydrator specifically tailored for us, food engineering students, has provided hands-on learning experience and opportunities that we can use on our future endeavors. This helped us comprehend how food dehydrators are built and how they work as a preservation method. Through this project, we have showcased our creativity by designing a viable food dehydrator that considers the choice of practical materials, heat transfer mechanisms, and control systems. Moreover, it provides us with knowledge on optimizing energy usage in food processing, a key aspect of sustainable and efficient food engineering practices.
By conducting this project, we were able to design and develop a portable food dehydrator. By employing the dehydration process on various food samples such as banana, eggplant, and chicken breast, we were able to discover the drying time of each sample. And we can say that forest can be further enhanced to ensure its viability for large-scale applications. From the selection of high-quality food-grade materials, which ensures its longevity and compliance with food safety standards, to its own unique features including wheels, handles, and a compact design which make it easy to use and transport. We believe that this dehydrator has the potential to meet the specific needs of the large-scale industry through collaboration with electrical engineers and industry experts.
The development of our food dehydrator has been nothing short of a collective achievement and a testament to the collaborative spirit that defines our team. At the heart of this endeavor is the power of teamwork. To each member of our dedicated team, the hard work and determination has been the driving force behind the success of this project. The diversity of skills, experiences, and ideas that each of us brought to the table has enriched the process and elevated the outcome of the project. The team would like to convey our sincerest gratitude and appreciation to various individuals who provided essential support in the development of this project. Our deepest gratitude is to our beloved family, especially to our devoted parents. Their aid and support financially, physically, and mentally enabled us to successfully finish this project. To Engineer Nicasio Pablo for the advice and patience that he provided us. Our gratitude is extended to him for his assistance, encouragement, and learnings in completing this project. We would also like to extend our gratitude to the Rosales Sash Factory for their incredible work in turning our sketch plan of the dehydrator body frame into reality. And lastly, to our Almighty God for the strength, wisdom, and guidance that He gave us throughout the conduct of this project.